My name's Derek Abbott, and it's a great pleasure to introduce James Chappell, who is a postdoc here in the department. He did his undergrad in engineering, then went off and did a PhD in physics, and now is back again in engineering. And he's going to talk about the square roots of zero. Take it away, James.
Thank you. Today, we think about the number zero as simply a location on the number line. Perhaps just a more satisfying start to the counting numbers. So we go NOR 1, 2, 3, 4. And we use zero as like an absolute mathematical zero as a starting point. In terms of the square root function, we can immediately recognise that the square root of zero is, once again, just zero. Hence the title of my talk, Much Ado About Nothing, the square root of zero. However, can nothing really exist? Indeed, several prominent physicists have promoted the idea that the net energy of the universe is exactly zero, where the positive matter energy being balanced by the negative gravitational energy. Alan Guth described the situation as the ultimate free lunch. A proposed explanation for such a zero energy universe is that the universe began from a fluctuation in the quantum zero vacuum state, leading to the Big Bang. Hence, the universe is eternally stuck at the number zero, at a point of zero energy. And so, even though we're at a state of zero energy, of course, we still exist. And for those adverse to complicated mathematics, you will be delighted to know I will only be dealing with the numbers 1, -1, and 0, and their square roots. Now, there's been quite a long and convoluted history of numbers. We began with earliest times with the basic counting numbers, 1, 2, 3, 4, 5, and the decimal place system was being used, but zero was just really a placeholder for the base 60 or the base 10 system. Square roots were also known in quite ancient times, beginning with the Babylonians. And it wasn't until the modern era, around 250 in the Common Era, that negative numbers were explored. And finally, our last number on the number line was zero. And Brahmagupta recognised it as a number in its own right and explored its properties. So only in 628 do we have our number system complete, so to speak. And then the square roots were explored. And famously in 1777 with Euler, square root of -1, which created a lot of controversy, but it was eventually accepted as a valid part of the number system. And it wasn't until 1870 by Peirce that nilpotent algebras, so-called, were investigated, which are the square roots of zero. So nilpotence is a simple idea. We just raise a number to a power, and if it hits zero, then it's nilpotent. And the roots of zero then are simply nilpotence of order 2. So a number squared is equal to zero. Now, if we think about that in terms of the real numbers, we think, okay, what squared equals naught? We might think, well, there's only one possible solution to that. That's 0, phi equals naught. And as a bit of a tangent, we won't go on, this sort of leads into quadratic equations, solving quadratic equations at 0. In case you think the idea of the square root of 0 is a bit pointless, it's got a very interesting application developed by Clifford in 1871. We wrote a number effectively, not a plus ib, but a plus the square root of 0 times b. And what that brings, very interestingly, is differentiation. that if you have a pretty well a general function and you do a coordinate substitution, switching from x to x plus the square root of 0, substitute that in, the square root of 0 part will actually be the differential. And so y prime is 2x times the square root of 0. So that is tagging the differential. And because most functions can be written as power series, that actually shows that this will differentiate pretty well any function, simply by using the square root of 0. And we can visualize that in 3D if we really want to, an x-axis, y-axis, and the one end of the page would be the square root of 0 axis, and we could plot simultaneously a function and its derivative. So let's explore this a little bit further. We want the square roots of 0, and we're not completely happy with just having one solution at 0. So let's just try a very simple trick. Just assume that the square root of 0 is some sort of composite number, x plus y. And we might think there of like the a plus ib as an example of a composite sort of number. But let's just leave it open, x plus y. So if we expand that, phi being our square root of 0 squared, expand the brackets, and we get, for that to be 0, we need x squared equals minus y squared and xy equals minus yx, which means they anti-commute. So we need x and y to anti-commute, and we need x squared equals minus y squared. And we might realise that that's true on the complex plane, where the reals have a different square to the imaginary parts. So we need some sort of numbers like that. And we actually can visualise this on the xy graph, and we need the vertical axis to have a negative square. So it'll have the negative square of the x. So it's very much like the complex plane, a real axis, imaginary axis, with the extra condition that x and y have to anti-commute, but that's basically saying they must be orthogonal. So that's effectively the visual representation there of the square root of 0. Now, for the physicists amongst us, you might realise that's very much like the light cone from physics, from special relativity, assuming that y is it, for example. So we've got a bit of an idea now what we need, and the way we're going to get it more precisely is using geometric algebra in 2 dimensions. Now, I did promise you we're only going to be looking at the numbers 0, 1 and minus 1. So in this case, we'd go for the square roots of plus 1. So we use 2 solutions, E1 and E2, where they both will square to plus 1. But as we said, we want them to anti-commute. And what we find is there's a bivector in there which squares to minus 1, which is what we needed, some sort of object that squared to minus 1. So we can immediately concoct a square root of 0 now as phi equals E1 plus E1 times E2, the sum of a vector and a bivector. So the E1 part will be the positive square and the bivector is a negative squared. And we just verify that as it's a root of 0, expand all that out, and we sure enough, we get a -1 from the bivector, a +1 from the vector, and because E1, E2 anti-commute, the whole thing goes to 0. So there's a root of 0, which is not 0. It's the sum geometrically. We can also visualize that. In geometric algebra, there's always a geometric visualization we can do. And our root of 0 is a E1, which is just a general unit vector, which we could draw any direction on the plane, plus a little unit area. So that's what this root of 0 looks like geometrically. Now, being good mathematicians, as soon as we have a nice simple solution, we try to make it more complicated. And the first thing we notice is that we can generalise it by putting a coefficient in front of each of the 2 terms, E and B, provided E equals B, because then they'll cancel out. I mean, also add a phase term, of course. So we call it K, we want k phi squared equals 0. And sure enough, if we make that k with an E2 exponent, and why that's going to work is because it'll anti-commute with E1 and it'll anti-commute with that as well. So when it anti-commutes, it'll change sign and cancel out, as we show down here. So that's still a root of 0, even though I have a leading phase term on it. So I've generalised the solution. So in physics, we call that like a gauge freedom, that it doesn't affect the solution. But what's interesting about it, if we just expand it out for a second with our leading phase term on the front of our root of 0, we get this gamma E minus this, which you might have seen before, which is the Lorentz boost of electromagnetic field. So in other words, the gauge freedom, which doesn't affect the solution, is all the Lorentz invariance. So we can say the Lorentz invariance is sort of built into the root of 0 automatically. What does that look like geometrically? Well, the phase term actually shrinks the vector and expands the vector and the bivector. So it just moves them out, but they still square to 0. So what we've discovered is the phase term is isomorphic to a Lorentz boost on electromagnetic field. And Lorentz invariance is thus an intrinsic property of the root of 0. And this property of fields wasn't discovered until 1200 years later by Lorentz, when he discovered this invariance of the electromagnetic field. So it's interesting how we've simply begun with 0, developed by Brahmagupta, and the well-known square root operation, and we've actually discovered electromagnetic fields and the Lorentz invariance. Now, as I said, we like to make things more complicated if possible. So we'll go to three-dimensional space now. And once again, we're going to use the square root of 1, which means all our unit elements squared are plus 1. And now we generate a new thing called a trivector, as it consists of 3 vectors multiplied together. And of course, a vector now it's got 3 components to it. So if we just consider again our square root of 0 in 2 dimensions, remembering it was E1 plus E1 times E2, if we write that in 3D, it's going to be E1 plus J times E3. And now we can see what it really consists of, which is 2 equal orthogonal vectors, E1 and E3. They are orthogonal. So now we can visualise rotating this generally into 3 dimensions, and so have a solution in 3 dimensions for the root of 0. So which will be over here, E plus JB, where E squared's got to equal B squared, and E and B are orthogonal. So that's now a general solution in 3 dimensions. And so generally, we can write this as now any vector plus J times any orthogonal vector, and there's an infinite number of orthogonal vectors to any vector in 3 dimensions. But provided they're orthogonal, we'll have a root of 0. Maybe I'll just jump up to this screen. So let's just check that this is going to be a root of 0. So we'll square it. We're going to get E squared. That'll be minus 1, so that'll be minus B squared. But E squared equals B squared, so that'll cancel. And this is basically the dot product, E dot B. And as we said, we make that orthogonal. And so that indeed is naught. And this null property actually is a well-known property of Maxwell's equations and electromagnetic fields. It's called the invariance of the electromagnetic field. And it's known to be like a null vector. So we're sort of reinterpreting it from the other direction and saying, interpreting it as a square root of 0. And indeed, this is a solution for Maxwell's equations, to have a vector and an orthogonal vector, one a vector, one a bivector. As we see down here, this is light in a vacuum, provided E equals B, and these two are orthogonal, which is exactly what we found from the square root of 0. So we can say that the electromagnetic field for light is actually the square root of 0. Exactly, including Lorentz invariance. So let's get a visualization again. So I've got the E. The E lies in the plane of the B, and the propagation is orthogonal to E and orthogonal to the B thing. So that'll show us what it looks like in 3 dimensions. We'll get a clearer picture in a minute. Just before we go to that picture, I could really stop there, and I would have thought that's nearly impressive enough that the square root of 0, it actually gives you the field for light. But actually, we can go another quite a big step, because instead of the field, we substitute in the bivector of the plane times the field, do that substitution, and we'll call that x. We'll find out what x is in a sec. And we substitute that through, and we get a scalar plus a vector. Now, in 3 dimensions, this will be a 4-dimensional object with a scalar and 3 vectors. The x bit will come from the E vector, and the scalar bit comes from the B vector. So, and you might recognize an object with a three-component vector and a scalar as a 4-dimensional space-time. And we can write this as just t plus x. And there's the, we can put the Lorentz invariance back in, which is slightly different now, but that's the correct Lorentz boost for the space-time. And for fields, that's the fields. You know, it's like a slightly different exponent signs there, because to make the square root of 0. So through that simple transformation, we actually get a 4-dimensional space-time object, which Brahmagupta wouldn't know what that was, but from hindsight, we can see what that would have been. Where we're once against the root of 0, so we have t squared equals x squared, which is the light cone now. But it's not a root of 0 the same way. It's x times x conjugate is what we have to use over the space-time. So as a key insight, the roots of 0 provide a natural pathway to show the origin of Minkowski 4-dimensional space-time and their Lorentz transformations. Space forms orthogonal to the E field, and times identified with the B field. So we can now sort of get a grasp on the nature and origin of time. So we found that the T component in the 4-dimensional space-time transforms from the B field. And if we think about it, Maxwell's equations actually show us that the B field is divergenceless. And so in other words, only has the curl in it. So, which means it's a purely rotational phenomenon, the B field. And as the B field rotates in electric in a helical path as it propagates, essentially time's also rotating with that, which is analogous to the hand on a clock. And we can talk about the phase invariances of 3D. Because we go to 3D, there's different types of gauge terms we can put on there, which basically are the Lorentz group, rotational freedoms and the Lorentz boosts show up there automatically. And let me keep moving along. And we sort of naturally produce a symmetry in both time directions, which is a well-known property of quantum mechanics and also leads to the Wheeler-Feynman absorber theory. Let me keep moving. So now, remembering what our solution was, E plus JB, where E and B are orthogonal, E equals B, and B is a unit area, a bivector, we can now get a very clear picture of what the square root of 0 looks like, which is the same properties we know for light. That there's a vector which lies in the plane of the so-called B field. The B field maps to the time, but the orthogonal vector to E is the K, or the X direction. And the invariances of that structure is invariant to a rotation. So it naturally rotates and forms a helical structure as shown, that E remains in the B, but they both rotate together in a helix. And really, this also introduced the idea of intrinsic spin, which is another quantum property we know about today. And I was looking to put gravity into here. It's not obvious exactly how to do that, but one way is a variable phase. The gauge freedom, make that a variable over space, which effectively means that the frequency will be a function of position, which could be interpreted as, say, a gravitational redshift or blue shift. So that's one approach to put gravity in. Sort of a related idea, once again, the roots of zero. Well, Einstein's field equations, as we know, lead to a static symmetric space-time solution, the Schwarzschild solution there. ds squared equals that. And of course, the roots of zero of that gives the light cone, and showing there a variable speed of light, 1 minus 2m over r, which has indeed been confirmed by the Shapiro time delay experiments. So hence the root of zero on the Schwarzschild solution give the light cone in gravity with a variable light speed, and similarly for general solutions. So that would tie in with a variable phase on the root of zero. And so we've done 0 and +1, now we do -1 a little bit. It's a way of generating geometric algebra that we want. Firstly, we want solutions of the square root of -1. In other words, objects that square to give a -1. And the first one in 2 dimensions is the bivector E1, E2, and that squares to -1. If we go to 3 dimensions, the trivector squares to -1, that's a root of -1. But if we try going an extra dimension to 4th dimensions, we find it stops working. It cuts off at 3 dimensions, which is obviously naturally matching the 3 dimensions we observe. So there's a picture of sort of the spaces we generate with the square root of +1 and the square root of -1, also called geometric algebra in 3 dimensions. So as a summary, since 628, when Brahmagupta came up with the 0 and the square root, if he'd been a very brave mathematician and sort of closed his eyes and just saw where the mathematics took him, this is the things he could have discovered. Firstly, the square root of 0, he would have found describes electromagnetic waves in the vacuum. And because there's a general phase possible, basically that implies the whole electromagnetic spectrum. And as we saw, circular polarization, and because it's all square root of 0, it means it's ubiquitous, which is basically, could be describing virtual photons. The phase term, he would have discovered Lorentz invariance back in 628 as a gauge freedom of his solutions. He would also could have inverted the transformations and found Minkowski 4-dimensional space-time and special relativity. Also, he would have discovered calculus as the roots of 0 give differentiation of functions. And circular polarization implies the property of spin. Yes, he would have found light comes from the square root of 0, implies some sort of active quantum vacuum as proposed by Dirac, Heisenberg and Feynman. His space-time would have emerged without reference to an invariant speed c, and implying it can be absorbed into units in agreement with modern treatments. Time arises from a transformation of the magnetic field, thus providing fundamental insight into its origin, and spatially varying phases would give gravitational effects such as redshift. So the connection between the concepts we've got is the roots of 0 gives us electromagnetic waves in the vacuum. The gauge freedoms leads directly to special relativity and Lorentz invariance. And from a transformation, we get Minkowski four-dimensional space-time and the origin of time. So since 1628, the roots of zero provide a purely algebraic derivation of the principles of special relativity. Mr. Chairman, do I have a few minutes to continue, or are we getting close to the clock?
You may continue.
Oh, thank you. Just give me a few minutes here, because there's something really interesting sort of appears on the horizon now, which is that our definition of a nilpotent actually can also be given as a definition of a triangle. Because we had phi squared equals naught, assuming it's a composite object. But this also defines a triangle. If we just think of phi as the hypotenuse, A plus B is two other sides. Look at our diagram here. Just let's go to the Argand plane, the complex plane, and think of these as complex vectors. C is A plus B as we draw in the complex plane. So this is indeed a definition of a triangle. Of course, in this case, the magnitude, it has to be C times C star, the conjugate. And as we discovered, we need to use the magnitude, this thing, C times its conjugate, as opposed to just the square. So why this works as a triangle is because it basically has closure, that C is the sum of those two. And if we just put an orthogonality condition on A and B, then we get a right angle triangle, which we'll find out what that is. So I've worked it all out here. That's the orthogonality condition for complex numbers. And it ends up being a complex dot product. If we use this as the dot product, where B star is the conjugate of B, then this will give us the definition of orthogonal complex vectors, to be correct. And this then moves down to a cosine rule for complex-sided triangles. And Pythagoras arises when we just simply make A dot B is naught, and then we get a generalized Pythagorean relation. The magnitude of each of them now sums to the hypotenuse squared. And so we've probably seen pictures like this, where they put the area on each side to show that the area of that plus the area of that equals the area of the hypotenuse. But why not make these areas functional? Why don't we make a triangle where the areas are independent of the lines? And in the plane, we've also got scalars or points. So on each side, we can have a point, a line, and an area on each of the three sides. And the advantage of doing the conjugate operation, as we found out, it's going to be Lorentz invariant. In this particular case, in two dimensions, it's always real magnitudes. And so generally it's real angles, unless we do sort of funny things like make negative side lengths and stuff. But generally speaking, it's real angles. And we've made each side now sort of functional. And these are our relationships. This will be the Pythagoras. That's the orthogonality condition. And the trigonometry looks more like this. And this is a particular triangle. I'm not going to read all this, but you can just note these are the three side lengths, A, B, C. Everything's integer, as you can see. And the magnitude is 4, 3, and 5. So all the magnitudes are integers. All the elements are integers, so it's a genuine Pythagorean triangle with A dot B equals naught. And we can look at these different types. Of course, there is a fourth type I've sort of forgotten about, which is isosceles triangles. But I found a very simple one in the first case, which is an equilateral triangle. B is 2, C is 2, A is 2. So it's 2, 2, 2. And it's got magnitudes 3, 4, and 5. So it's a 3, 4, 5 triangle in magnitudes, but an equilateral triangle in terms of length. So it's sort of a composite sort of Pythagorean triangle. And there's little pictures of a few different ones I've discovered. And So it's an interesting task to try to find all the different types of triangles and the smallest ones, and etc. So there'll be whole classes of different Pythagorean triangles. Now, once again, how can we make this more complicated? So go to 3 dimensions, of course. Now, in 3 dimensions, we're going to have an 8-dimensional object on each side of the triangle. And got much more complicated magnitudes. Also, the angles will be now complex. And I've given you an example here. There's possible 8 numbers go in there because we want integers. The magnitude is complex, as you can see. But the magnitude a squared plus the magnitude of b squared is equal to the magnitude of c squared. So it's a Pythagorean type triangle, and everything's integers, as you can see. And so that's the general relationships for our Pythagorean relationship. There's a picture. There's the magnitude. As you can see, everything's integers. And what it sort of is 2 superimposed 3, 4, 5s in this case. So we have the vectors can form a triangle, and the bivectors can also form their own independent triangle. And those two are superimposed, forming a general Pythagorean triangle in the magnitudes. I think I've got an animation of that. There we are. So there you go. There's a 3-dimensional Pythagorean triangle, a 3, 4, 5 one in this case, in fact. You all had enough of that one? It just goes back and forwards, but as you can see, that's and there's many more types with different ways to superimpose the vectors and the bivectors together to form Pythagorean type triangles. So the beauty of these sort of triangles is that they're invariant, which means for any observer they'll also see the fact that it's Pythagorean, and a right angle triangle will remain a right angle triangle. And this has, I'll just jump through to the applications, which is triangles might seem like an abstract idea, but actually they have a lot of important applications, such as particle collisions, which come to a point and then diverge, say, into 2 separate particles. Well, that's a triangle which has to conserve momentum and energy. Of course, in force analysis, in trusses and whatever, that have set multiple forces coming in, they have to all balance out to a triangle. Electrical circuits with phasors, Feynman diagrams, everything has to conserve at the vertexes. And we can generalize this further to 4-sided polygons and to other sorts of algebra, such as Cayley-Dickson. And so a lot of interesting things to work out here, like to classify all the types of 3-dimensional Pythagorean triples, mixed Cayley-Dickson algebras, to interpret what a complex angle actually means, that if a triangle has a complex angle, how do we interpret that? And applications to different physics and collisions and conservation principles. So I thank you, Chairman. That's the end of my talk. If there's any questions.
Thank you very much.